We'll get started in a couple of minutes, but hope you can hear me and see my screen clearly. Good evening. Welcome to the week 7 live session. Great. We'll wait one more minute in case people are still joining and then get started. Okay, let's continue. So, this is the week 7 live session, and for anyone who's joining for the first time, this will be a 2-hour session. Interaction will be through the chat window. Post the session, you will get access to the slides and the recording, so don't worry about that. And feel free to ask your doubts and questions on chat. And we'll take a 5-minute break roughly around 8 o'clock. So let's get started. So in week 7, we mainly looked at reduction kernels and optimizations on these kernels. So we started off with what is a reduction operation. Then we looked at how to do some common reduction operations in a parallel fashion so that you can exploit the GPU's parallel CUDA cores to do this. And then we started from one version of the reduction kernel and continued finding some performance bottlenecks and proposed some optimizations to overcome those bottlenecks. So we saw around 6 to 7 such optimizations for one reduction kernel, and we also did a performance analysis of all those optimizations. So we looked at the time it took for execution for each of these optimized kernels, and we also spoke about why there was an improvement, or in some cases why certain things were problems, right? And then we looked at 2 other examples, the bitonic sort and the prefix sum. And here also we kind of looked at the algorithms and proposed some optimizations. So broadly, today's discussion will cover these topics. Other than some doubts and questions from the previous week, most content will be centered around this. So let's get started. So we'll do a quick recap, just a few topics, just so that you remember the basics and you can answer the questions. So let's start with reduction, right? So what do you mean when you hear the term reduction? So it refers to reducing a vector to a single value. And I think this was not highlighted in class, but this is something interesting, right? It says via an associative operator. So this is not maybe strictly covered in class, but it will be good to think about why it mentions an associative operator. Think about this. Would it work? Would all the things that we discuss work if it was not associative? And in case you don't remember what associativity means, so for instance, in addition, taking a simple operation, you know commutativity and associativity, right? A plus B equal to B plus A. And similarly, on 3 things we define associativity, A plus B plus C. So we talk about operators for reduction that are associative. So in case the associativity property does not hold, think about what would happen to reduction as such. So after this session, maybe think about one example where the operator is not associative and try to write like a simple handwritten example of how the reduction would go on. That's just for your own curiosity. But some common examples of reduction are sum, minimum, max, average, and or. So what does a reduction do is it visits every element in the array and then performs some operation on them, right? Now, why do we want to do parallel execution of this reduction? Basically because again we have a large array and we want to also exploit the parallelism of the GPU. Also notice that it says reductions are not compute bound but memory bound, because these are all very simple computations usually, right? For instance, if you consider a sum, you take two inputs and perform one operation, right? So the memory activity of this operation, reading two operands, is actually more intensive than the computation itself. Added to that, there is the problem that compute is much faster than memory, right? So the time it takes for the compute might be very small. Let's say something like 1 microsecond, right? And the time it takes to read these two from memory might take 5 microseconds. That's why we also in some cases try to increase the work that you do per thread, right? You want to somehow kind of increase the compute or increase the work that you do for every memory read, and lots of things like that. But broadly, reduction operations are memory bound, not compute bound. Moving on. So we see a simple example of a serial and a parallel reduction. So here we are computing the total sum across this array. So in the sequential version, it's a simple, think of it as a simple for loop, right? Where you keep adding this current element to the sum. So there is one thread that is doing this operation, right? So there it's not done in parallel basically. So at one step you would do one addition, and then in the next step the next, and so on till you get the total sum. So this is the sequential version. Now you can also think of a parallel, and this complexity of this is order of n. So if you have n elements, it's going to take linear time to compute the sum. But if you come up with a parallel version where now you have multiple threads, in this example for instance you have 4 elements and you have 2 threads. So notice that thread 1 takes element 1 and 2 and performs a sum, and at the same time thread 2 can perform a sum of 3 and 4. Then you just add both of these together and you get the sum. So notice that what took 3 operations here, or 3 steps rather, is now taking 2 time steps, because 2 of these operations are happening in parallel. And similarly, if I had 8 elements, I would have 4 additions here, then 2 more additions here, finally 1 addition. So this would be 3 steps, right? So the time complexity of this is order of log n. So if it's 8, it's log to base 2 of 8, which is 3. Whereas here you would take 7 steps. So that's the difference between the sequential and the parallel. So moving on, now we've kind of seen why we need to parallelize, right? Now coming to the GPU programming side of things, how would you do this? So if you have a very large array, then you can't have this many threads dealing with things, right? So you will need to have multiple blocks, and every block will reduce a portion of the array. But now the problem is you need to communicate these results between blocks, and that needs global synchronization. And CUDA does not support this. I think we studied in the earlier lectures itself that global synchronization is kind of a limiting factor to scaling. So that's the reason why CUDA does not support that. So instead, what can you do? You can decompose the kernel itself. So what we do is we take the computation and break it down into multiple kernel invocations. and this kernel launch serves as some kind of a synchronization, right? That's the broad intuition over how we are doing this. So with that, yeah, I think we have one more recap slide. And coming to how do you measure performance? So if it's a compute bound kernel where compute is the bottleneck, we will look at gigaflops per second, which again I think we spoke about it earlier also, which measures the number of floating point operations per second. And if you're talking about memory bound kernels, we look at the bandwidth. So you would have noticed that in the example kernel taken in class, we looked at both of these metrics to see how our optimizations improve the compute part of it and the memory part of it, right? And many times, and I think we didn't look at gigaflops per second, we just looked at execution time. So execution time would be affected both by the compute and the memory. So whenever, for instance, we improved the memory bank conflicts, you would have seen that the execution time went down, right? Similarly, if we did some optimization on the compute side, the execution time will again go down. And yeah, this also we discussed again. It's just one floating point operation. For instance, if you think of an addition, right? If you load an element, you just do one flop per element that you load. So this is called arithmetic intensity. Basically, if I load one element, what computations am I doing with that one element? Maybe I have 10 lines of code and I have to do all of this for one single element. So then what would happen is this kernel or this operation might become compute bound, because you're doing one load and that will take some MB, some bandwidth or some memory to load this element, right? After that, you perform n number of computations. So let's say this is maybe 10 flops, right? So the arithmetic intensity would be much higher for something like this. Whereas reduction typically has just one flop for an element that is loaded. So we say it has very low arithmetic intensity. Therefore, we have to strive to get the peak bandwidth. Otherwise, it will take even longer to do this load. So think of this pipeline like this, right? So you do a load and then you do a compute. I think we saw some pipeline diagrams in the initial classes. So let's say this is like this. Now, if I take 10, some unit of time, 10 microseconds to do the load and 1 microsecond to do the compute, then the load becomes very critical to optimize. The higher our bandwidth is, we can reduce this load time to some extent. Maybe we can make it 7, maybe we can make it 5. And the overall time depends a lot more on this load because the compute is very small. That's what this is trying to tell you about. So this is true for reduction operations in general. Yes, with that, I think we're done with a quick recap. So was there anything else in week 7 that was not clear to you, something that you didn't understand? I can explain it in detail in the next class. I'll just wait for a minute here to see if any of you have doubts. Anything in week 7 content that was not clear, feel free to mention it. You can take a few seconds to quickly look through the slides if you want. And if there's anything at all that you haven't understood or that you're confused about, feel free to post a message on chat. Any questions? Okay, if not, let's keep moving ahead. So next we look at a couple of questions that were asked on the discussion forum. So these have been already answered by the TAs. I'll just be discussing them here in case you've missed it or in case you didn't understand it quite well. So this question is about the week 7 assignments question 3. So the person who asked it says there are two correct options. A bitonic sequence is decreasing at first and increasing, or vice versa. And the TAs have answered that there is indeed a mistake in this assignment 7 question 3, because of which there are two correct options. So the assignment will be re-evaluated accordingly. So they can't change the question at this point. So answer it the way you want to, and if there are multiple correct options, I'm guessing both will get marks. So this should be straightforward. The other question that was asked, since we are making each thread to load data from location I and I plus block dimension dot x, should we not check if both of these fall in the range of n? So you may have noticed some checks in some reductions where these I or I plus block dimension is checked as whether it's less than n, right? So this person is asking in the reduction 4 in the kernel that we picked up as an example, this was not done. So why was it not done is the question. So the answer that's given is this observation that there needs to be a bound checking is correct, and this has been omitted just to keep the pseudocode short and clear, right? So typically if you were writing this program, it is good to have the bounds check. They have just left it out, not really for correctness issues, but more as a matter of shortening it. Okay, the last question. So this is about the grid size, right? So this person says, as far as I could understand, grid size means total number of threads in a grid, which means number of blocks in a grid into number of threads per block, assuming a 1D launch. And grid size should have been equal to block size into grid dimension of x. I'm unable to understand why we are multiplying 2 in this calculation. As per the discussion, each thread is loading the sum of 2 memory locations, but does that increase the grid size by a factor of 2? And just so that you have some context about what grid size calculation we are talking about, I've pasted part of the code here. So this is what the person is asking about. Grid size is taken to be block size into 2 into grid dimension dot x. And then, excuse me, in this loop, you're trying to add g of I data of I and g I data of I plus block size. And then your increment is by grid size. So this is the framework by which you interpret this question. Now the answer given is a bit detailed, but let's go through that step by step. So here's an example. Assume that we have to add 256 elements, and we know that every thread adds 2 elements in this reduction, right? And we want to assign more work to be done by the threads, and we set the parameters as follows. So block size is 32, number of blocks equal to grid dimension dot x, which is 2, and grid size equal to 128. So for now this is an assumption, right? Block size into 2, so you know block size is 32. So if you do, and you know grid dimension is 2, so 32 into 2 is 64, into 2 128. We've not spoken about why there is this into 2, but let's just take this grid size to be this, and this is 128 in this example. So now in the first iteration of the while loop, this while loop, the first 128 elements will be accessed and added. So threads from the first block will access elements from 0 to 63, whereas threads from the second block will access elements from 64 to 127. And in the second iteration, we increase the value by grid size by 128. So the next 128 elements from the input will be added. So now threads from the first block will access the again 128 plus 64 and then the next 64, right? So, and this is why, since we are doing this, so the definition of grid size does not change. The factor of 2 comes because of each thread accessing 2 elements, right? And because of that, once your one set of accesses are done, the increment should not be by just block size into grid dimension. It should include this factor of 2, right? Because if I just do 63 or 64, that wouldn't be enough because every thread is going to access 2 elements. So I should actually do 128. So that's why there is the factor of 2. So this is kind of the reason why we have a factor of 2 coming in. I think that is the last one. So were these 3 things clear? Any further questions on any of these? I'll just pause 30 seconds. One mark was not added to this question. Oh, the solutions were released, is it? Okay. So I don't know how they were the solutions released before this question was answered on the forum. Okay. So they might not have noticed it then. So I'm guessing that they would be manually correcting this in their tally of marks. So many times it happens that all of this is automated, right? So they might have put in the solutions and released it, and they would have noticed that something is wrong only when someone pointed it out. So they would go and make that correction manually, and it would not necessarily reflect to you in the portal. But you can again confirm that in case, maybe wait 3 or 4 days if this was just reported, and then after that, once maybe a week has passed, you can check and see if check and see what they say. My guess is they would do it manually, but you might not be able to see it on the NPTEL portal. Yeah. Okay. With that, okay, we had 2 more doubts from the last week. So these doubts were from the assignment week 6 assignment questions. So question 2 and question 3 were asked. So let's start with question 2. So memory bus utilization is calculated as number of bytes requested divided by total number of cache lines loaded. Consider a case in which a warp requests 32 consecutive 4-byte data elements that are not aligned. The addresses requested by the threads in the warp fall across two 128-byte segments in global memory. Assume the architecture has an L1 cache enabled and L1 cache line size as 128 bytes. The bus utilization in this scenario is 100, 50, 25, 3.125. So this is the question. So the answer was 50%. So let's see how that is, right? Here the number of bytes requested are 32 into 4, and that's 128. And L1 cache is enabled and L1 cache line size is 128 bytes. Now we are told that these addresses are not aligned. So what do we mean by aligned? So this alignment concept you will see in multiple places in multiple subjects, and it broadly means the same thing, right? So we have some boundary or some granularity, and we are talking about whether a particular data element is exactly at that boundary or it is offset from something. So let's take a simple example, right? So operating system has something called pages. If you've studied virtual memory and memory management, you'll be aware that there are these things called pages, right? Now let's say the page size is 4 kilobytes, 4 KB. Now if you request data, that if let's say you request 4 KB and the 4 KB is page aligned. So what do I mean when I say page aligned? It starts where the page starts. So then this 4 KB is going to be just one page, right? Now if I say that this 4 KB is not page aligned, then what it means is it could start in the middle of this page. Let's say it starts somewhere here. So 2 KB is in this page and then 2 KB is in some other page, the first half of some other page, right? It might so happen. So now the same 4 KB of data will take you 2 pages. So this is broadly the notion of alignment. Now in this case, what we are told is the addresses that are requested by the warp fall across two 128 byte segments, right? So these 4 addresses fall into 2 segments. So now how many cache lines do we need to load? The segment size is also 128 byte and the cache line size is also 128 bytes. So we just need 2 cache lines. So now going back to the formula, number of bytes requested is 128, 32 into 4, divided by total size of the cache lines loaded, that each cache line size is 128 and you load 2 cache lines because this is not aligned. If it was aligned, then one cache line itself could have been sufficient. But because it's not, it's 128 divided by 128 into 2. So that's basically half, and to get it in percentage, you multiply by 100, which gives you 50%, and that's option B. Now is this clear, or are there any doubts in this? I'll pause here for a few seconds, go through the solution and see if you understand it. Okay, if there are no questions, let's move to the next doubt that was asked. Again, it's a very similar problem. So consider a case where all threads in the warp request the same address 4 bytes and the architecture has L1 cache enabled and L1 cache line size is 128 bytes. In this scenario, the bus utilization is, right? So now you have 4 bytes that are being requested. So the numerator is 4 and that would be in one cache line. So total cache line size requested is just 128 and then into 100. That gives you 3.125. Is this clear? Okay, great. So then I think this is all we had. But since we are kind of at the midway mark in the course, right? Week 1 to 6, we have covered all contents. So, are there any topics from all 6 weeks that you're still not sure about or that you're kind of struggling to understand? That would also be a good thing to bring up. That way, in the next session, I'll spend some time because we just have 12 live sessions, right? And then your exams also would be right after that, I'm guessing. So, if you have any, okay, question 2 again, sure, I will do that. Right. So here, what we are told is, so there are th- there are 32 consecutive 4-byte data elements that are requested, right? And we are told that these addresses fall across two 128 byte segments, right? So this is segment 1, this is segment 2. Now these 4-byte, maybe they fall something like this. So out of this 128 bytes, let's say for simplicity, 64 bytes are in this segment 1 and 64 bytes are in this segment 2, right? So to get these 128 bytes, it is not enough if I load just segment 1 or just segment 2. I will have to load both of them. So although you, in theory, your warp is requesting only 32 into 4, 128 bytes of data. In practice, because of the way that data is organized in physical memory, you actually end up loading 256 bytes, right? You're loading double. And if this was, say, scattered in 4 segments, then you would end up loading all 4, which would make it 512, right? Something like that. Basically, just like this example, the example of the page thing that I told you. But here we are told that it is spread across 2 memory segments. So you know that if you load both of these memory segments, you will get all of this data, all of these 32 consecutive 4-byte data elements, right? So now putting this back into the formula, the number of bytes requested, basically what your threads in a warp have asked for is just 128 bytes. They have asked for 32 into 4 by 4 bytes, right, which is 128. And but how many what is the size of the cache lines that are being loaded? You're loading 2 cache lines because this is present in 2 segments. So the total size of cache lines loaded is 128 into 2. 128 from here, 128 from here, right? So 128 divided by 256 into 100 gives you the utilization. That's 50%. So basically, out of the 256 bytes that you're loading, you're only using 128 bytes because that's all you need. But you have to load this extra because it is not aligned. If this entire thing was present as one segment, then you would get 100% utilization because you load 128 bytes and you are requesting 128 bytes. So that's 100% utilization. You use all the data that you load. In this case, you load 256 bytes, but useful data out of that is just 128 bytes, right? So that's a 50% utilization. Okay, hopefully that was clear. And before we move to today's problems, I'll pause again. I was asking if there are any topics that are kind of difficult for you guys to understand. Please mention them in chat. I'll wait for a minute because we are kind of at the midway mark of the course, right? We finished 6 weeks of content. Today we'll be finishing one more. So rather than waiting for the last session to ask all your doubts, it would be good to ask them now so that I have the time to address them in the next session. Session wise problem sets to practice besides what is being discussed in the lecture sessions. Right now, I think that's what the live sessions are intended to do. But like I mentioned in the last class also, this year there seems to be a lag of 2 weeks. So so basically whatever we discuss in these live sessions, are your practice problems. Besides this, there are no practice problems that I am aware of that I can kind of provide you a link to. So these live sessions will help you for the final exam, but for the assignments, you have to kind of go through the course material and try to do it on your own. That looks like that's the way they have intended the live session schedule. But lecture wise questions marked from the reference book, again, I don't know that. You can ask this on the discussion forum once to see if the instructors or the other TAs have an idea on this. I am not really familiar with the reference books mentioned, so I can't unfortunately point you to practice questions from there in this format. But live session problems are definitely intended as practice problems for you. They'll definitely help you for. Right. Yeah, I've read Hennessy and Patterson, but I think there is only a few chapters on the GPU architecture, right? So I'm not sure if how much of the practice problems there would be relevant for you, and some of it might help you understand these topics better, but they might not necessarily help you solve NPTEL exam questions, because these exam questions are in a certain format. Like you've noticed, all of them are MCQs, and all of them mostly involve applying these concepts to solve numerical questions, right? So questions from these books may or may not help you directly do that. So I'm not sure if there are practice problems that you can work on that will help you with these. But feel free to ask this on the discussion forum as well once, because the instructor and the official TAs will also see those questions, and if they have some suggestions, they might tell you. Sure. But any particular topics that are not clear, or where you feel many times you look at the questions and you're unable to solve on those particular topics, that I can help by maybe going through that topic once more and then picking out a couple of questions on those topics. Do we get similar assignment problems in the exam? As of what I am aware, I think you do, but I can just check that once and let you know. I am not sure. I think it should be very similar to these, but I'll just check once with the official TAs and let you know in the next session. Sure, I'll do that. Otherwise, how is the course going for you guys? Are you able to solve the assignment questions, or does it feel very difficult? Just generally asking for feedback, no particular reason. Okay, I see, difficult. Yeah, I can imagine this is an advanced course, right? So it's not very intuitive to solve the questions without having some sample questions, right? But let's see, what can we do? If time permits, I can. So I think we have a lag of 1 or 2 weeks, right? So in the next session, maybe if I can cover week 8 and week 9, maybe we can catch up, something like that, right? I can try maybe, or maybe I'll have a combination of a few week 8 questions and a few week 9 questions. That way, at least it will help you solve the week 9 questions ahead of time. But beyond that, I don't think there's something I can do. I think it's more about how they've scheduled it. I think last year the sessions were kind of uh, starting right when the course started, so it was very aligned. So it would be that your assignment deadline is a few days after the live session. So that way, the live session really helps you solve very similar questions. But we can try this out and see how it goes. Next week, I'll try to have some problems from week 9 at least, if not all of them, so that at least some of your assignment becomes a little easier. Okay, so if nothing else, we'll move to the problem solving. Okay, here's the first question. Consider an array A where A of I equal to 1 if I is divisible by 2 and A of I equal to 0 otherwise. The array has 1, 0, 2, 4 elements. Let us consider a reduction which computes the addition of all the elements of the array. What is the final value of this reduction operation? There are 4 options. I'll give you 2 minutes to think about this. Solve it, and then when you have an answer, you can post it on chat. Any answers so far? I think this is fairly simple. So we need to think of what the elements of the array are, and then you know what is the reduction, right? You're told that the reduction is addition. So now if you add all the elements of the array, that's basically the question. If you add all the elements of the array, what do you get? Now think about it if you were struggling to understand the question. Here's a hint. Okay, we have one answer that says 512. Anyone else? Did anyone else get the same answer? Do you have a different answer? Okay, we have one more answer saying 512. Okay, let's take a look then. So it is 512. So let's look at this, why it's 512, right? So A of I is 0 or 1, that's what you're told, based on the divisibility of 2, right? So we don't even need to know when it is, it's basically, if it's even it's one thing, and if it's odd it's one thing. So you have 1024 elements, out of which 512, because it's an even number, right? So there are equal number of even numbers and equal number of odd numbers here, right? So half the elements would be 0 and half the elements would be 1. That's basically what it comes down to. So now, given that the reduction is addition, so you're going to add all of these elements in different orders, of course, but ultimately the operation performed is addition. So you'll add all the zeros and you get a 0, and you add all the ones and you get 512. So the total sum is 512. Now is this clear for anyone who didn't understand it before? I'll just pause here for a few seconds and then move to the next one. Okay, I'm guessing that was clear. Let's move to the next one. Consider the same array A with 1024 elements where A of I is equal to 1 if I is divisible by 2 and 0 otherwise. Now consider the same reduction kernel but with the XOR operation, right? Not addition. What is the final value of this XOR reduction operation after applying it on A? Now think a little more carefully. It's no longer simple addition, it's XOR. So try to remember the XOR truth table as a first step and then try to reduce this array. Again, I'll give you 2 minutes. Think about it. Okay, we have an answer saying 1. Anyone else? Think carefully. XOR is easy to get wrong. For people who don't remember the truth table of XOR, so if you have a 0 and a 1, right, in any order, that is whether it's 0 XOR 1 or 1 XOR 0, the answer would be 1. And if you have two things that are the same, that is if you either have 0 0 or 1 1, the answer would be a 0. Now try and solve this. So from last question, you already know that 512 elements of A are zeros and 512 elements are ones. Now think about what happens if you reduce it. Anyone? No answers? Okay, let's take a look. The answer is 0. So why is that? Again, remember that from last question we said that A contains an even number of zeros and an even number of ones. So for simplicity, we'll just take 4 zeros like this, right, and 4 ones like this. Now if I apply XOR here, I get a 0, I get a 0. Then let's say I apply XOR here, I get a 0. Similarly, I get 0 here, I get 0 here. Finally, I get a 0, and then I XOR these two, and again I get a 0, right? Now, you might be wondering, the order is not like this. The order is actually going to be something like 1 0 1 0 1 0. But again, try doing that as well. You will still get the answer to be 0, because finally if you have two ones next to each other, remember that it XORs back to 0. So the answer here is going to be 0. Any doubts on this? Is it clear now, or does it still seem very confusing? Okay, it's clear. Okay, then let's move to the next question. Again, consider the most naive version of the reduction kernel being launched with number of threads in a block as 1024 on an array of size 2 power 24. How many times should the reduction kernel be invoked from the host program? This is slightly different from the previous question, so take some time and think about it. Take 2 to 3 minutes and then we'll look at the answer. Any answers so far? So you're given the array size, you're given the threads per block, right? You're asked how many times should this kernel be called. So think about when the reduction completes, right? The reduction takes an array of some size and converts it to one element. So basically the reduction should be called as many times as it needs to reduce this entire array to one element. Now think about it, how many times should it be called? Anyone? Okay, we have one answer, 3. Anybody else? No other answers? Okay, let's take a look at the answer then. Someone is still solving it. I'll just wait for another 10 seconds and then we'll look at the answer. Okay, so it is 3, so that answer was correct. So in the first iteration, you have 2 power 24 elements, and this 1024, the number of threads, is basically 2 power 10. So the elements get reduced to 2 power 24 divided by 2 power 10, which is 2 power 14. In the next iteration, it reduces from 2 power 14 to 2 power 4, basically 2 power 14 divided by 2 power 10. And then finally in the third iteration, this 2 power 4 2 power 4 elements also fully reduces to one element. So the reduction completes. So there are three calls to this reduction kernel. That's your option E. Is this clear? Okay, at the third time. Right, so if that is lesser, right? So basically your reduction terminates when the number of elements comes to 1. So as long as you see a fraction that is lesser, like 2 power 4 divided by 2 power 10, then it means that the reduction terminates in that operation, in that iteration. So it would be just 3 iterations. It might not need the full iteration, right? It might not need all of these 2 power 10 threads, but we are launching them anyway. So it will finish in the third iteration. Okay, hope that's clear. So we are at 8:02, so I think we can take a 5-minute break. So see you guys at 8:07. I'll keep the call running, but feel free to get some water or walk around so that you're not overwhelmed by 2 hours of continuous listening and absorbing things, right? And if you have doubts in anything that was discussed so far, feel free to go look up the lecture slides, and then once we come back, we can talk about it. See you at 8:07. Okay, let's continue. So we were done with question 3. Let's move to question 4 if there are no doubts on that. It's a very similar question. Consider the most naive version of the reduction kernel being launched with number of threads per block as 64 on an array of size 2 power 24. How many times should the reduction kernel be invoked from the host program? 4, 6, 8, 12. Again, take a couple of minutes. Okay, we have one answer saying 6. Anyone else? I'll wait 30 more seconds if someone else is working it out. Okay, we have one more answer, 4. Anyone else? Okay, let's look at the answer. It is 4. So let's see why. Alright. So here number of threads per block is given as 64, which is 2 power 6. Right? And your array size is 2 power 24. So just the way we did the last question. So here we did 2 power 24 divided by 2 power 10, which means that the exponent reduces from 24 to 24 minus 10. So each time there is a minus 10 that happens to the exponent. So that's what this answer says. Like here there is a minus 6 because your number of threads per block is 64, which is 2 power 6. So first your exponent is 24 because your array size is 2 power 24. After the first iteration it reduces by 6. It becomes 18. Basically it is 2 power 24 divided by 2 power 6, which is 2 power 24 minus 6. Right? In the next iteration it goes to 12. Then in the next iteration it goes to 6. And then it goes to 0. So 2 power 0 is 1, which means that the size of the array is now 1. which is what a reduction does, right? It takes an array and reduces it to a single element. So how many iterations did this take? 1, 2, 3 and 4, right? And if you had to come up with a formula to do this, it would be ceil of exponent of the array size divided by exponent of the uh, block size, right? So here 24 by 6 is 4 and ceil of 4 is just 4. In the other case, for instance, it was 24 divided by 10, right, which is 2 if you take an integer, right, and then you do a ceil of that, you get 3. So that's why it was 3 iterations there. Here it is straight away 4 because 24 is a multiple of 6. But this is a convenient formula in case you want to save time and calculate it directly. But this is the logic behind it. Hopefully both are clear. Any doubts here? Okay, if this is clear, we'll move ahead. Okay, very similar question. Consider the version of the reduction kernel. Okay, note this down, where the first addition operation occurs during initial global load kernel being launched with the number of, there's a comma or full stop missing here. Where the first addition operation occurs during initial global load, terminate there, and the kernel is being launched with the number of threads in a block as 32 on an array of size 2 power 12. How many thread blocks are launched in the first invocation of the kernel from the host program? So notice that there's something different asked here. You're asked for how many blocks are launched in the first invocation of the kernel from the host program. And you're given the number of threads per block. You're given the array size. And you are also told that the first addition occurs during initial global load. This was an optimization we had studied in class also, right? Now think about this, take 2 or 3 minutes to solve this and then we'll discuss. Okay, we have one answer saying 128. Any other answers? I'll wait, I think a minute more at least. Take into account that the first addition occurs during the initial load itself. Okay, 64. Any other answers? Anyone else? Okay, let's look at the answer then. So it is 64. So how does it come out to be 64? So if you have total number of elements to be n, you launch a total of n by 2 threads, right? we saw this in the example that we studied in class. Now, given this, in the first iteration, so your array size is 2 power 12, right? So 2 power 12 divided by 2, which is just 2 power 11, right? So in the first iteration, you would launch 2 power 11 threads. But the question is, how many thread blocks are launched? And you are given the number of threads per block as 32, which is 2 power 5. So the total number of blocks is the number of threads divided by threads per block, right? So 2 power 11 divided by 2 power 5, which is 2 power 6. That gives you the number of blocks or thread blocks that are launched. So the only difference here is you're asked for the blocks. So you have to take the total number of threads and divide it by the threads per block. Total number of threads is 2 power 11 and threads per block is 32, which is 2 power 5. So you divide 2 power 11 by 2 power 5 and it gives you 2 power 6. Any doubts here? Okay, if not, we'll move to the next one. In question 5, how many thread blocks are launched in the second invocation of the kernel from the host program? So the same kernel, everything remains the same. Number of threads per block is 32. Array size is 2 power 12. We spoke about the first invocation of the kernel. Now we are asked about the second invocation of the same kernel. Again, take a couple of minutes and think about this. We have one answer saying 32. Okay. The question is, how many blocks are launched in the second invocation of the kernel? Anyone else? We'll wait one more minute. Think about it a little more. Any other answers? Does everyone else agree with 32? Okay, let's look at the answer. It is actually 1. So let's see how that is. So when we left off after the first invocation, we said that there would be n by 2 threads launched for n elements, and in this call we figured out that we need 2 power 11 threads. Similarly, let's go to this question, right? So now the array in this iteration, in the second invocation, the array size gets reduced from 2 power 12 to 2 power 6, right? And how many okay, this is not second iteration, this is in the first iteration. It gets reduced from 2 power 12 to 2 power 6. So right now you have 2 power 6 elements, right, at the beginning of the second iteration. Therefore you need to launch half of that, which is 2 power 5 threads. You need to launch 32 threads for 32 for 2 power 6. Okay, this shouldn't be threads, this should be elements. Maybe I will just correct that before I forget, or maybe I'll do it a little later. But let's just read this as elements for now. So we are launching 2 power 5 threads for the 2 power 6 elements. But remember that the block size or the number of threads per block is 32. So the question is, how many blocks are launched? 32 threads are launched. So the block size is 32. So your number of blocks is 32 by 32, which is 1. I'll repeat this since I think the first sentence was, I said second iteration. So in the first iteration, remember here that we started out with 2 power 12 elements, right? So we reduce that to 2 power 6 at the end of the first iteration. In the second iteration, for those 2 power 6 elements that are left over now, we launch 2 power 5 threads. But the question is not how many threads are launched in the second iteration, but how many thread blocks are launched. And you know that block size is 32. So how do you get number of blocks? Total number of threads divided by block size. Total number of threads is 32, block size is 32. Therefore, it's just one block that needs to be launched in the second invocation. Hope this is clear. I'll pause here in case you need a few more seconds to look through the solution. Do that. Okay, I'm hoping this is clear. If not, please ask. Okay, it is 1 if block size is fixed as 32 for both the cases. Is that correct? Yeah, block size is fixed too because we are taking the same data as this question, right? So the array size also remains the same. The block size also remains 32. Okay, I think I get why you're asking. There probably was some example in class where the block size also changed, right? Is that why you're asking? Right. So yeah, for this question, I think we need to assume that the block size remains whatever is mentioned in the question. If they are referring to one of those instances where that changes, then they would mention that particular reduction. For instance, uh, in this place they mention where the first addition occurs during initial global load. Similarly, they might refer to that particular reduction version where the block size changes. But otherwise, assume that it remains whatever is given in the question. Okay, sure. Let's move to the next one. In question 5, so this is the same data we're talking about. How many times in total is the given reduction kernel invoked from the host? 1, 2, 3, 4. Take a minute to think about this. We already spoke about the first and second iteration. Think about whether you need an additional iteration or those two are enough. Think about it. Any answers so far? Okay, 2 if the initial load is done earlier. Yeah, we assume still that it's the same reduction kernel where the initial load is done earlier. So, okay, your answer is 2. Anyone else? We'll wait for another few seconds and then look at the answer. Okay, let's take a look. It is 2. So remember again, in the first iteration we reduced from 2 power 12 to 2 power 6. And now that we have 2 power 6, we said we are going to launch 2 power 5 threads. And this thread block is sufficient to reduce that given array, right? So 2 iterations are sufficient in this case to reduce it to one element. Therefore, the answer is 2. Any doubts here? Okay, if not, we'll keep moving ahead since we have less than half an hour left. Which of the following statements is correct? Inclusive scan of an array generates a new array where each element j is the sum of all elements up to and excluding j. Exclusive scan of an array generates a new array where each element j is the sum of all elements including j. Bitonic sequence is a sequence of numbers which is first strictly decreasing, then after a point strictly increasing. In the most naive version of the reduction operation, half the threads are idle on first loop iteration while executing the kernel. Which of these is correct is your question. Okay, D is correct. Want to know about other options? Okay. Anyone else? Right. So the answer given here, again I've taken this from the official answer key, is D. In the most naive version of the reduction operation, half the threads are idle on the first loop iteration. But I think that C should also be considered, because I think there was this. So according to the definition given in class, bitonic sequence is a sequence that first strictly increases and then strictly decreases, right? But I think from the discussion forum, I think the same question was present in week 7, and I think that was the discussion forum question that we just discussed. Does anyone remember that? Is it the same question? Yeah, this was the one, right? Yeah, so that means that C is also a correct answer. So the official answer key was modified. So bitonic sequence can also be defined as this way, right? Where the order is opposite. It's first strictly decreasing and then strictly increasing. So the official TAs also said that both are accepted answers here, right? So C and D would remain valid. I will highlight both of them in green before I upload the final version. So for now, you can take both of them as the answer. And A and B are not correct, because inclusive scan would be including this element, and exclusive scan would be excluding that element. Both of those are wrong for that reason. Is it clear now? Okay. Let's move ahead then. Okay, consider the following reduction kernel code snippet. Reduce 1 is the kernel name. So thread ID and I is defined as usual. Block id.x into block dimension.x plus thread id.x. S data of tid is also defined in this usual way that you've seen in class. And for s equal to 1, s less than block dimension of x, multiply s by 2 every time. If thread id mod 2s equal to 0, s data of tid plus equal to s data of tid plus s, after which you have a sync threads. And then finally, if tid equal to 0, g o data of block id x dot x is equal to s data of 0. So this is the kernel. Now the question is, which of the following is correct? The kernel suffers from divergence. Warps in general are inefficient in terms of utilizing the hardware. Half the number of threads are underutilized from the first iteration itself. All of the above. So this was a kernel that was discussed in class also, if you remember. So try to look at the code and think about which of these are true. Divergence, warp inefficiency, and half threads are underutilized, all of the above. I'll scroll back here. Think about it. Take a minute. Any answers so far? I hope you've seen the kernel. Let's move to this part. Okay, let's look at the answer then. So it's all of the above, right? Let's think about why. So let's start with the first point, right? Branch divergence. So let's go back here. So let's say this value is 4, right? Now think about this TID mod 4 equal to 0. Basically, it's a multiple of 4, right? So one thread in every 4 will satisfy this. The other 3 will not, right? So the divergence is definitely there, and as this stride increases, as s keeps getting multiplied by 2 each time, so next it becomes 8. So one thread in every 8 will satisfy this condition. So that's why it is definitely divergent, and it's highly divergent, right? Then so if you remember this part that was used in class, right? So this is this first reduction 1 that was discussed in class. So it is definitely very highly divergent, and the warps are also inefficient, because in a given warp you don't have a lot of per thread activity. That's why in the later optimizations we try to do more work per thread. So the warps are inefficient. Additionally, at every iteration half the threads do nothing, right? So that's also a problem. And so all of these are true. A, B and C are true. So the problem with this reduction kernel is all of the above. That's why its performance is so poor, and that's why we propose a lot of optimizations on top of it. Hope this is clear. Which question? This 9, is it? Question 9 was part of assignment 7, is what you're saying, and it had an answer different from this. Okay, I was not aware of that. I think I looked through it. Uh, okay, check. Okay, question is entirely different. Okay, then I don't know if the answer that was given is correct. So if you have a doubt in one of the answers for assignment 7, again ask that on the discussion forum. I just looked at it and it looks like the solutions are released, right? So if you think one of the solutions is wrong, again ask for a clarification on the discussion forum, and they will respond in 1 or 2 days. I will also check in parallel whether the same question was there as part of your assignment, or if it was a different version. And next class, in case you haven't heard back on the discussion forum, I will definitely address it. If not, I'll just go through whatever answer they've given. I don't know if it is the same question as of now. I am unable to see it. So yeah, let's not do that while I'm discussing the questions. I don't think we have the time. So it could be a different question. You please verify that and then ask on the question, ask on the forum. Okay, moving on to the 10th question. Okay, consider the following reduction kernel code snippet. So again, I'll skip over some of the initial things. So S data assignment looks like this, and within your for loop, you do something differently here. You do index is equal to 2 into S into TID, and if index is less than block dimension of x, state of index plus equal to state of index plus s. And then there's a sync threads and there's the same global data updation. So for this kernel, which of the following is correct? High divergence, shared memory bank conflicts, slower than the reduction kernel in question 9, none of the above. Think about this. Any answers? This was also discussed in class. I'll scroll up again if it helps. So the options are high divergence, shared memory conflict, shared memory bank conflicts, slower than the kernel in question 9, none of the above. So this is the kernel. Any answers? Okay, let's take a look if you're not sure. So it is the kernel suffers from shared memory bank conflicts, right? Let's see why that is. So this was the second reduction, right? This was an optimization that was put to make it slightly better. So now you can see that it's no longer divergent. That's the first thing. So if you see the way the code is written, you can see that that modulus operation that was there is changed to this, right? Index less than block dimension of x, state of index plus equal to state of index plus s. Now because of this, there is no longer a divergent branch here. So that first problem is eliminated. And moving forward, talking about shared memory branch conflicts, now your thread 0 is trying to access something from bank 0 and bank 1. But you have something, some other thread here, thread 8, which is trying to access the same bank 0. And for every bank, you will see that there are two threads that are kind of accessing that, because of which there is a conflict, there is a bank conflict. So that's the reason this is true. And this is not slower than the kernel in question 9 because we have improved the high divergence. We've also removed this modulus operator that is very slow. So if you see here, the reduction 2 is actually faster than reduction 1. This warp inefficiency is also now gone, right? So this option is false. So the only thing that is true is the shared memory bank conflicts. Is this clear? I'll wait here. Okay, great. If so, we can move. I think we have one question left. So this is very similar to the first couple of questions we discussed. Consider an array A where A of I equal to 1 if I is divisible by 4 A of I equal to 0 otherwise. The array has 1, 0, 2, 2 elements. Consider a reduction which computes XOR of all elements using a binary XOR operator. What is the final value of this reduction operation? 0 or 1? Think about this again. Okay, 1. Anyone else? I'll wait a minute more and then we'll look at the answer. Okay, 0. Okay. Yeah, this whenever there is an XOR and yeah, it can get a bit confusing. So think about it if you want a little more. Another 10 seconds and we look at the answer. Okay, the answer is 1. So let's see how that is. So this is a detailed thing given here. I won't go through it in too much detail because we did a very similar question, but feel free to work this out and use these to verify if you're along the right direction. So first step of reduction, the 1022 becomes 511, and again you have a few ones and you have a few zeros. The second set, notice that it no longer becomes pairs of things, right? So you have 255 pairs and a single one. This is the interesting thing. Then in the third cycle, so this becomes 127, and again there is one element left over and another element left over. So you have a set of 127 sets and a single 0 and 1. Similarly, in the fourth cycle, you have 63 sets and a set of 0 and 1, 31 sets of zeros and 0 and 1, and finally, the 10th cycle you end up with a 0 and 1, and in the 11th cycle you end up with 0 XOR 1, which is 1. So the answer is 1. But feel free to work this out in detail. I don't think it is difficult. If you just spend a couple of minutes, I think you can figure it out. But if you still don't understand, feel free to ask me and we'll spend some more time on this. Okay, with that, I think we've come to an end of the questions. So, yeah, this is all I had for today. We still have some time left. So, in case you have any other doubts or questions, put that on the chat. I will wait for another a minute or two before I end the call. So, feel free to use that time to ask your questions. I will definitely address them in the next week. And if you don't have any other questions, thank you so much for joining and hope to see you next week as well. Hope you're finding these sessions useful. Okay, question 5. Sure, let's do that since we have a little time. Okay. So this was the reduction kernel where the initial global load happens and number of threads in a block is 32 on an array of size 2 power 12. How many blocks are launched for the first invocation of the kernel? So you have 2 power 12 elements in the array. So if the number of elements is n, you launch a total of n by 2 threads, right? So in that same spirit, if you have the array size to be 2 power 12, you launch 2 power 11 by 2, basically half the number of threads, right? That gives you 2 power 11 threads. Now the question is how many thread blocks are launched. So number of blocks will be total number of threads divided by threads per block. I'm just going to write this as threads per block. So total number of threads here is 2 power 11 and threads per block is 2 power 5 because we are given that as 32 here, right? So 2 power 11 divided by 2 power 5 would be 2 power 6. So your number of blocks would be 2 power 6. Now is this clear? Okay, great. So I'll wait for another 30 seconds in case you guys have questions. If not, thank you so much for joining. See you next week. How many questions do you have? Again, I'm not sure, and I'm not sure if that's something fixed. I will ask and see if I can find a previous final exam or something like that. But this, I don't know if I will get a straightforward answer. I will check, like I said, whether they'll be similar to your assignment questions. I can check on the format of the questions. Number of questions, not very sure. If I get to know, I will let you know in the next class. Sure, no problem. Okay, if there are no other questions, we are 4 minutes before time. That's good. So, thank you so much for joining and see you next week. Bye.